Hello everyone, this is Brian, recording a project briefing video for CSC 143. In Project 2, we're going to be implementing a doubly linked list. A doubly linked list is much like a singly linked list with an addition to every node, such that each node is now going to point back to its predecessor node in addition to its existing reference to its successor node. Another way of looking at that is that every node is now aware of both its left and right neighbors. For this project, your task is to implement a complete doubly linked list that provides a list-like interface with operations like insertion, deletion, and iteration in both directions. You're going to be using a lot of references to track and organize the internal data that's stored within these nodes. And you're going to discover how big O, runtime performance, is going to change based on a client's needs and how much that client inserts versus iterates over the list. As usual, you can grab the project starter code from this download link and open it up directly in IntelliJ to get started quickly. Let's go over the interface I'd like you to implement for this doubly linked list. We have the linked list class, which is a generic type. Inside the linked list is going to be a list node that I'll give you for free that simply is a container for a previous and a next. We have some constructors for this linked list, including the empty constructor, which starts as an empty list, and the iterable constructor, which is going to convert an existing iterable container into a doubly linked list. Then we're going to find a list of methods I'd like you to fulfill. These methods are going to be much like the methods that we've explored so far on lists. Peek front, peek back, these are going to examine and return the value at the front and the back of the list respectively. Pop front and pop back are going to remove and return the front and the back of the list respectively. Methods like push back and push front add items to the list. This add method, which takes an integer argument, is going to add an item to a specified index in the list. On the flip side, the remove method that takes an integer argument is going to remove a specific index from the list. Then you're also going to provide iterators, which will fulfill using the linked list iterator and the linked list reverse iterator internal classes. As you can imagine, the iterator is going to iterate forwards and enable clients to use the for each loop, as well as invoke methods like next and remove to examine and even remove items from the list. The reverse iterator is going to do the same thing, but in the reverse direction. We'll start from the tail and iterate forward to the head, which is possible for us because we have a doubly linked list and every node has a reference to its predecessor. In addition to the methods and classes I'd like you to implement for the doubly linked list portion of this project, I've also thrown in some bonus classes that I'd like you to develop based on your linked list implementation. These classes are the stack and the queue. In these bonus classes, we're going to explore the distinction between containment and extension. Containment is when a class contains another class, and that class has access to the public methods exposed by the class interface. Extension is when a class extends another class, and that class automatically inherits all the public and protected methods of the parent class that it can invoke immediately. I'd like you to have an understanding of how containment and extension expose different interfaces to the underlying classes involved, and what the implications are when it comes to external clients who are planning to use our classes. We'll start out with the stack class. We've talked about the stack before. Remember that a stack is like a stack of plates in real life. Items that are pushed onto the stack have to be removed in reverse order. The stack implementation is going to contain a linked list as a private variable and leverage the linked list's public interface to support all the stack operations. I'm asking you to implement methods that you would expect in a stack like push, pop, peek, and size. The queue is like a queue in real life. It's like a line of people. People who enter the queue end up at the end, and people who were first to enter the queue are first to get removed. The queue implementation in this project should extend the linked list instead of contain a linked list. We're going to leverage the methods exposed by queue we're going to leverage the methods automatically inherited by the linked list to support these queue operations. We're going to implement methods that we would expect to see in a queue, like add, remove, peek, and size. However, there is one additional layer of complexity with extension. Unlike the stack, queue should not reveal methods that modify its internal state and disrupt the expected behavior of the queue. So what I'd like you to do, if there's a method that the queue unintentionally exposes because it's a child of the linked list, is to override those methods and throw a runtime exception. Remember that by nature of queue being a child of linked list means it's going to get a lot of methods for free, but it's also going to get some methods that are not so desirable on a queue structure, such as insertion into the middle of the queue. That's something like the equivalent of cutting in line in real life. When there are methods like that the queue exposes, you should go ahead and throw an exception so that when a client tries to call it, they get an exception in their code. Now let's turn to the source code and take a look around. You have got the linked list class, the base class for this project, and the embedded list node class that just contains a next and previous reference as well as a payload value. I'll give you some starter fields, the front node and the back node, which are the head and the tail respectively, and a size value that you should remember to update anytime you add values to the list. And then I've just got a whole bunch of method declarations that I'd like you to fill out to go perform the list operations that's expected of them. Down here, I've already added the iterator method, which should of course return this linked list iterator instance, which is going to support methods like next and hasNext. Remove is a method that you may have not seen before on an iterator, but it is a method that is on the iterator interface. And what remove is going to do is it's going to take out the element we're currently referencing inside the list during iteration. What I mean by that is, suppose we're using an iterator to iterate over the values of a linked list, and we stop at value at index I. I can invoke the remove method on the iterator to remove the ith element from the list. This is going to involve some additional complexity with your iterator, because it has to be aware of not just the node it's iterating over, but how to remove the node with access to the neighboring elements. What I don't want you to do in the remove method is to just call this remove of index method here on line 66. The reason for that is because this remove of index method is designed as if it was being called externally, and we have to loop to go reach the index node that we're looking for in order to remove it. Instead, given that we will already have access to the node we're currently iterating on, we should be able to do the removal in place. We should be able to just examine the left and the right neighbors and remove the node without having to perform additional iteration. I've declared this remove of list node method here where you can implement that. I believe this method is actually optional. You don't have to implement it, but I do recommend you implement it. So you have a way of removing a node in place without having to iterate to go reach that node at a particular index. In addition to the iterator method and the iterator instance, I'd like you to also do it in backwards order. This reverse iterator is going to return an instance of linked list reverse iterator, which, as you can imagine, is going to behave the same way as the linked list iterator that iterates forwards, but instead navigate from the tail of the list to the head of the list. Okay, now let's go take a look at the queue and the stack. We'll start with the stack first. Here, the stack is a bonus class that you can implement for some extra points. It's going to contain an instance of a linked list, and it's going to invoke methods on the linked list. On the flip side, the queue is going to extend the linked list and automatically inherit linked list methods for free. At the same time though, the queue has to go hide the methods that it doesn't intend to expose, because those would enable external clients to violate the integrity of the queue. I'll go ahead and let you explore that on your own time. As usual, I've offered you a complete test suite for evaluating the success of your linked list. I always recommend that you start from the bottom, or well, the top of the file, and make your way down. And as the tests get more complex, so too will your implementation. This final test, the linked list test, is a sort of integration test that's going to evaluate all of your linked list methods. We'll start out with this constructor that accepts an iterable type. Your linked list will store 0, 1, and 2. I'll do some things like push back, push front, and remove. Make sure the size gets updated. Then try iterating over the list, removing elements via the iterator call, and expecting that the list continues to be updated. Once you've passed this last test, you should be happy and give yourself a pat on the back, because this means you've successfully completed all the methods that the linked list asks of you. Now, this might seem a little bit overwhelming at first, but I want to reassure you that over time, as you figure out the manipulation of references and how to modify the data inside the linked list, you're going to get more and more comfortable with dealing with each of the cases that you're going to encounter. As an example, let's talk about the case where we're inserting an item into the linked list. Suppose for a moment that we had this method insert that accepted an argument index, which specified the location of the list inside the list that the element needs to be inserted into. We know that we definitely have to construct a new node, but how we wire up the neighboring pointers as well as its own internal pointers is up to the circumstances and context in which that node is being inserted. If the list is completely empty, for example, this new node that we're inserting becomes the new head and the tail of the list because it's the only node inside the list. In the case where we're inserting to the back, maybe index is exactly equal to the length, or maybe it just so happens the index is equal to 1 and our list size only contains one element at this point. We have to make sure to update the new node's predecessor to point forwards to this new node we're inserting, as well as update this new node we're inserting to have its predecessor point back to the neighboring previous node. Things get complicated when we try to insert in between two existing nodes. Suppose for a moment that this node on the left here and this node on the right here were the original neighbors, and we were trying to insert a node in between these two nodes. We'll have to construct our node, wire up its internal references to point back to the previous node and forward to the successor node. Then we'll have to rewire the previous node's successor node to point to this new node, as well as the next node's previous node to point back to this new node, essentially eliminating the original references that had connected those two nodes together. There's of course a lot more cases to think through and a lot more methods to write, but that's the nature of the project, and I'll let you go try and work on it. Okay, as usual, the project specification contains everything you need to know, hopefully. If you have any questions, don't hesitate to ask on Piazza and email me, and I'll try and get back to you as soon as I can. Thank you for listening, best of luck, and I'll talk to you next time.